All right, gang, as you could tell from the previous video, I was kind of going back and forth about whether to demonstrate backward elimination or stepwise regression in general. And I thought that it's actually a pretty good idea because, you see this from time to time, and it's quite possible that some of you may justify using backward elimination in your to analyze your data for your master's thesis. So, uh, looking at the data set that we've used, this OT grant, you can see that I only selected 4 or 5 predictors, but actually I think there are 17 predictors there. Well, the theory tells me that I need around 15 cases per predictor. So if I have a sample size of 30, I can't, or at least I shouldn't use any more than 2 predictors. Well, for this data set, we have 244 subjects. So if I take 244 divided by 15, this tells me that I can comfortably go up to about 16 or 17 predictors. So I thought, because you see a lot of people do this, let's just throw all the variables in the model, run this backward elimination, and see what it determines, it being R, determines as the optimal model. And again, we're looking for the not losing too much in terms of our percentage of accurately classified cases, our model, our potential for accurate model classification, but limiting the subset number of the subset of the number of predictors. Easy for you to say. So anyway, I think there are 17 here. Well, we got 2, 4, 6, 8, 10, 12, 14, 17 predictors. So I've thrown them all in the mix, and we can see that we have 2 predictors that are statistically significant. Feel, this is a feeling inventory. I forget exactly how that was measured, and age is still a statistically significant predictor. Now, the ones that emerged pretty high, this p-value of 0.90, open 8. I don't remember exactly what that was, but I suspect once we start the backward elimination process, R will eliminate it first, reevaluate the model. If it doesn't quote unquote do any harm to the model, then we'll eliminate the other one, and the process will continue. Now, let's look at the percentage of accurately classified cases with all of these predictors. So I could look at the predicted probabilities for my model, and I want those to be at the standard threshold of 0.5. So anything greater than 0.5 will be true. Anything less than 0.5 will be false. And I want my dependent variable, which is false. So my percentage of accurately classified cases will be 116 plus 50, okay, divided by 244. So 68% percentage of accurately classified cases, not that impressive. Again, we like to see that up around 0.80, but it is what it is, and we would report that. Now what I want to let R do, or force R to do, is to create a backward model. And I use a step function, which is included in the base R package. And I begin with the full model, which I calculated above. And then I perform what's called a backward elimination. Now, let me explain to you what backward elimination does. Probably just exactly what you would think it would do. It takes the entire set of predictors and will keep removing a predictor until it gets to a point where it is doing quote unquote harm to the model accuracy. I'm going to turn the trace function off because I don't need to see what happens at each step. It really clutters up the R output when I do this. So let's go summary backward and see what R determined as the optimal model. So it determined so 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 predictors as the optimal model. And of the 9 predictors, it looks like close 6, feel, can you stand without help, and age are the statistically significant predictors. Now, let's run the table. So let's do fitted for backward, still with false. And our percentage of accurately classified cases will go down. But again, there's just a trade-off there. We allow the percentage of, or we don't allow it. We are okay with the percentage of accurately classified cases decreasing somewhat, just not quote unquote too much. So PAC here, well, I'm not going to write that out, but it would be 111 plus 45 divided by 244. So our percentage of accurately classified cases went down about 4 percentage points. But nevertheless, we have a lot less predictors and a more manageable model than before. So if I were taking this approach, what would the summary of the results look like? I would, just as I did with the previous example, I would report the full model. It would be a kind of a messy table, but I would go ahead and report the full model down to presenting the coefficients. I would go through the test of the assumptions, variance inflation factors, the interaction of the variable with with the log of the variable. The model diagnostics that I present early on, sensitivities, specificity, percentage of accurately classified cases, the whole thing. But once I get down to the table of the coefficients, then I would state the summary for the reduced model. And I would use the reduced model only to calculate the area under the curve and present the receiver operating characteristic graph. So I may ask you to do this in a homework assignment. I really haven't decided yet, but I'd say more than likely, someone who I advise in their master's thesis will use this approach. All right, keep thinking that forgetting to tell you something, but I don't know what it would be. This video is intended to be complete because I've done the complete example previously. I've done an example previously. This is just to give you kind of an insight, let you see what actually happens with stepwise regression. I will say this, you could perform a forward direction. So I call it a frontwise stepwise regression, where it will start out with one predictor, and then it will test all the others and then add the one that would create the lowest p-value, and then it'll add another, and then it'll just keep adding predictors until it gets to an optimal model according to some threshold working behind the scenes in R. Gang, it's all I got. Take care. I wanted you to see this.